So today we're going to continue to talk about chapter 8. Let me start sharing with screen with you. And so here are the stuff we talked about yesterday. Chapter 8, as I said, we focus on rotational equilibrium. Okay, so this is kind of like a chapter 4 of Newton's law, but we care about rotation now. Okay, so we start from mechanical equilibrium, which is defined as something at rest or in constant velocity. So in that case, the total force equal to 0. So normal force equal to gravity. Normal force equal to weight. Well, when you have something that has a potential to rotate, you need to have an additional condition to take care of that possibility. And that is where we need this new quantity called torque, which is the only quantity we want to introduce in this chapter, and the quantity you guys need to learn, And it's defined as force times distance times sine of the angle theta, where theta is the angle between the direction of force and direction of this distance that connecting the rotational axis and the acting point of the force. And basically we're saying that in order to produce a rotation for something that's not in rotation, you need a torque, okay? You need a non-zero torque to produce rotation. We give you some example here. So when you have a force that's acting directly on the rotational axis, you won't have a torque. So you won't rotate something. Or when you have a force going along the direction of this distance here, like this case, you won't have a torque. So you won't rotate the object, okay? In other cases, you would have a torque, okay? And this is very similar to the idea of work that we learned before. Again, the angle theta, it matters a lot in this case, okay? For the case of a torque, the distance d matters as well. You need to have a non-zero d, and you need to have a non-zero angle theta in order to get a torque, okay? And the torque is a vector. You can either rotate something counterclockwise, which means tau larger than 0, or clockwise, meaning tau is smaller than 0. So the rotational equilibrium conditions, we have two conditions. First of all, the total force has to be 0. That's the same condition we had in chapter 4. This makes sure that the object does not move in the hole, okay, altogether. Well, secondly, you have to have the total torque equal to 0 as well. This makes sure that even though the object does not move in the hole, it might rotate around one part of it, like in the case of a door rotating around the hinge, or a wheel rotating around the axis or something. But if you have total torque equal to 0 on the object won't rotate. So these are the two conditions we have for rotational equilibrium, okay? Again, these are like the principle we have in this chapter, okay? In solving problems, we use this again and again and again and again, okay, in different settings, okay? Well, you may have different torques in those different problems, but in the end of the day, you're checking for these two equilibrium conditions, okay? So we did one example about the balancing the pencil, like we demonstration, right? We showed that when you have a force, when you put your finger underneath the middle, you can balance it like this. But because in this case, you can satisfy both these two equilibrium conditions. Well, if you put your finger on one end of it, it cannot satisfy this equilibrium conditions. It's either, so this thing gonna rotate, so it doesn't matter how big the force you have here, it's still gonna rotate because there's gonna be a non-zero torque, okay? And then we talk about example 8.8, this seesaw problem, right? So the seesaw problem is actually probably agrees with your intuition. You kind of know already without taking this class, right? If you have two objects on the two sides of the seesaw, normally the smaller mass need to be staying further away from the rotational axis, while the larger mass staying closer to balance it. So that is actually okay. Let me go back to the white screen here. So basically, what we're saying here is, okay, hold on. Let me pull out the drawing option. Okay, so for a seesaw, right? In general, okay, like this. Say there's something balanced at the middle, right? Something balanced. So they're basically two torques if you have two objects, okay, on two sides of it. Now, well, the seesaw itself has weight and there's normal force, but they acting on the rotational axis, so there's no torques of these two forces. So these two forces have zero torque. Now the only two forces you have torque is this one and this one. So if you call this one M1G and this one M2G, based on, I mean, let's call this L1 and this is L2. Now, according to the this problem, and then the total torque is zero, I mean, the balancing torque, you end up with the equation like M1G L1. Okay, this is the torque make it go clockwise, so it's negative. And then this is M2G L2. This is the torque make it go counterclockwise. Sorry, this is, I don't know what this is a positive, this is negative, okay? So M1G L1, this make it go counterclockwise. M2G L2 make it go clockwise. So this is negative, this is positive. The sign, you have to put it by hand. So these two torques together equals zero. Notice there's no sine theta here because theta equals 90 in this case, okay? 90 degree, 90 degrees. So sine theta is just one. So it's just the force times distance, okay? So total torque equals zero, like as we see here, right? And then from there, you can write M1G L1 equals to M2G L2, okay? Well, this is a very, it is a pretty useful formula for balancing the seesaw or something. But again, you do not need to remember this formula. This is just a specific formula for a specific setup. Well, this is the principle you have, okay? Total torque is zero. So basically saying that if the mass is small, the lengths need to be larger in order to have the same torque for this. So for a smaller mass, you need to put it further away. For a larger mass, you need to put it closer so that these two can balance each other, which kind of makes sense, right? I mean, I guess it agrees with your intuition, okay? Do you have any questions before I move on about this situation? No, good, okay. Let's do some other examples because we have time and because this is almost like the last topic that's gonna be on the test, you know? So let me do some other example, then we'll do a exercise together today. So the example we want to do here is, maybe we'll do two of them, okay? Let's do this one first, okay? Don't climb the ladder problem, okay? The ladder problem, okay? In this case, you have a ladder that's kind of leaning toward the wall like this. Now you're given the length of the ladder, which is 10 meters, and then the weight, which is 50 Newton, okay? Now it basically is saying that the ladder is just on the verge of slipping when it makes a 50-degree angle with the ground, okay? Find the coefficient of static friction between the ladder and the ground. So it's kind of like if you make it a little bit, leaning a little bit more, it's gonna slide. So it's just like the marginal point for sliding to happen. So this is barely making it like 50 degrees. So okay, let's do this together on the whiteboard, okay? Sorry, this is example 8.10, okay? So we have okay, we're given here is the weight of the ladder, which is 50 Newton. We're also given this angle, which is 50 degree. We're also given the length of the ladder, let's call it L, capital L, which is 10 meter. So that's 3 pieces of information. Now we need to find out the coefficient of static friction. Well, again, this seems like a little bit odd, right? I mean, how come it's related to the coefficient of static friction, okay? So let's try to understand this situation, do some analysis to solve the problem. This one's definitely a little bit harder than the previous one we talked about, previous example, okay? So, so what is going on here, okay? Well, we know, so again, we should start from a free body diagram, okay, for force analysis on the ladder, you know, because otherwise we wouldn't understand what's behind it. Okay, so this is the ladder right here. Now certainly there's always gravity, right? So you should always start from gravity. And remember, the gravity is acting at the center of gravity, which is basically at the middle, the geometrical center of the ladder. And then we have two contact with the surface, to the horizontal one and to the vertical one. Let's start from here. Because it has horizontal contact, so there definitely going to be a normal force. So let me use the same, okay, so same notation. So let's call it N here, okay? Well, there's another normal force from here because this has contact with surface as well. So the book used P for this force. I will call it P as well, okay? Now, another condition that was not, I forgot to mention this, uh, the wall, the vertical wall is frictionless. So there's no friction on there. Well, it may not be realistic, but it's simplify a little bit for us the problem. So there's no friction on this wall here. So we don't need to worry about friction. However, there is a friction on the surface, okay, of the ladder because there's no motion here. The friction is static. Okay? So which direction does the friction go? Well, if you just look at this, right, from the force point of view, there's a one force that pushing the ladder to the left. So there, you must have another force to balance this force. Otherwise, the whole ladder is going to go this way. So there's the friction should go this way. Okay, Fs. And this is a kind of common sense as well. You know, there got to be some friction on the surface. Otherwise, the ladder will definitely slide, right? I guess if you have any experience climbing up a ladder, you definitely know what I'm talking about, you know, and you really care about this. Otherwise, because you worry you may slide off, you know, when you're on the ladder or something. So there that you want to put your ladder on a point, on some spots on the ground that has sufficient friction there. You don't want to put it on ice or something, you know, so they're gonna easily slide, or on a wheel. You don't want to have a wheel here, you know. So anyway, so these are the four forces we have. Okay. Well, as you see here, it is definitely more complicated than the previous case. Well, one thing I want to emphasize here is when you do problem in this chapter, when you do free body diagram, draw the forces, draw them at their actual acting point. Okay. In chapter 4, we were saying that for convenience, you could draw everything starting from the center, you know, like this, and you know, and all the forces do not change when you move them to the center. Well, that's just because there's no rotation we need to worry about in those situations. When you need to worry about rotations, you need to draw the forces at their actual acting point, okay? Otherwise, you won't be able to get the correct torques, okay? So anyway, this is our setup, okay, for these four forces, okay? Now, what does mu s has to do here, okay? Anything mu s has to do. Now, it turns out because it's a marginal case, so that means you just move a little bit further, the ladder is going to slide. That means your coefficient, your friction has reached the maximum value. Okay, as we know, the maximum static friction equals to mu s times n. Okay, so you need this formula here. Okay, because you're reaching the maximum static friction. Otherwise, I mean, you wouldn't say that when you slide a little more, the ladder is going to slide off. So so you have this. That's why you have mu s here. Okay, and this is something we want to figure out, right? So how do we do this problem? Again, we have start from your principles. The principle you have is either for this ladder to be at rest, you have either you have both a total force equals 0 and total torque equals 0. Okay. Let's just write down equations based on this. Let's start from total force. Okay. Now there are two directions here. Some force is going horizontal, some force is going vertical. So you can set up your coordinate system like this, x and y, and set up Newton's law for each direction. Along the x direction, you have two forces. You have Fs going positive direction minus P going negative direction. Okay, that equals 0. So that's one equation. Along the y direction, you have normal force and gravity. So normal force going up, gravity going down. So this together equals 0 again. Okay. And then, so that's it for the total force. Okay, so we take care of two directions. Let's talk about the total torque. Okay. Now to calculate torque, you have four forces, right? But remember, to calculate torque, you need to start from a rotational axis. So, well, you can choose any points as a rotational axis. Normally, we choose it as a point that's most convenient for us to solve the problem. Which point do you think is best for this problem? We can choose this point here, or the middle one, or the left corner, middle, or the right corner. Which point do you think is best? Send me a message. Yeah, just guess, you know. Okay, I got one answer so far. Okay, the point is you want to choose the rotational axis such that it can reduce your labor of doing calculation, you know, as much as you can, meaning that you can easily tell some torques are zero, okay? So you don't have to calculate all the 4 torques, okay? So actually, in this case, this point here on the left is the simplest choice for the rotational axis, because if you choose this as your rotational axis O, the normal force and the friction will have 0 torque because they have 0 distance crossing this point. So these 2 torques are 0, so you don't have to worry about them. There's only 2 torques given by the P and the mg. If you choose this actual rotating axis, you need to calculate 3 torques. Same thing, if you choose this, you calculate 3 torques. So this one is the best, okay? So only 2 torques, okay? So we'll write, again, for this torque P, this is gonna make it go clockwise, sorry, counterclockwise, so it's positive. For the mg, it's gonna make go clockwise, so it's negative. So you have these 2 torques. One is positive, one is negative. Let's set up the equation together. So for this one here, so you have the force, which is P times distance. What is the distance here? Okay. Well, because P is here, right? So the distance is simply the length of the ladder. Well, what about angle theta? Well, in this case, angle is not 90 degrees anymore. It's actually this angle right here. Okay, this is the angle here. Okay. Well, we are given this angle theta here, which is right here, right? So according to geometry, this angle and this angle are equal. So this angle is theta as well. So you just multiply by sine theta here. Okay. This is making it go counterclockwise, so it's positive. Okay. Now another torque given by mg. So you have mg here as the force. The distance here is simply half of the length of the ladder, so L over 2. And then the angle, what is the angle here? Well, it's going to be this angle, right? This angle is not theta, but because this angle is theta, so this angle is 90 minus theta. Do you agree? This is 90 minus theta, right? So you should write sine 90 minus theta, okay? And then there's a minus sign here because this force makes it go clockwise, so it's a negative torque, okay? So together, this equal to 0, okay? So we got these 3 equations. Well, we actually have another one here because we know the relation between the friction and the normal force, right? So this is one as well. So in this one, we have 4 equations. Well, it looks a lot of equations, but you should feel confident that you can only solve those equations, okay? So what should we do? Okay, we're interested in mu s here, right? To get mu s, we need to know n and fs maximum. Well, to get n, we can use the second equation we have here. So we got n here. To get fx maximum, we have the first equation, but that requires to know p. So to get p, we have the third equation here. So basically, it's like we can get n and p from this, and then we get fs maximum, and then we get mu s. So let's start from the second equation, okay? So the second equation, we got n equals to mg, with mg is given as 50 Newton. So just 50 Newton here. And then we do the third equation, we can get p, okay? So let's plug a number right here. So by the way, L cancel out here. So you have p times sine 50 minus mg over 2. Remember this L is canceled out. So it's sine 40, okay? So basically P equals to mg over 2 sine 40 divided by sine 50. Okay, so that's the answer for P, okay? So let's calculate it. So you got 20.977. So you basically got 21 Newton, okay, for the P. I got a message here. So okay, that's fine. Okay, so we got this P here. And the next step is basically we can go back to equation 1 to get Fs maximum, right? Because according to equation 1, Fs maximum equals to P, which is just the 21 Newton, okay? Finally, we can use the force equation to figure out mu, okay? So because first we have Fs maximum equal to mu s times n. So basically mu s equals to Fs maximum divided by n. Okay. So that's 21 Newton divided by n, which is 50 Newton. Okay. So that's basically 0.42. Okay. Let's divide this. So we got our coefficient of friction. Does that make sense to you guys? Okay, let's check our answer here. Yeah, 0.42. So that's correct. Okay. Well, this looks complicated, and actually, I think in the test or in the homework, we normally have simpler problem. This is a little bit complicated problem for you guys, you know. So, but I want to give you a complicated example to show you like how the, hopefully this whole thing is not totally new for you because we're kind of similar to what we did for Newton's law. Okay. If we keep the numbers here, I mean, if we keep the symbols here, we can get a more interesting result. So, for example, if we take here, you know, we know P equal to mg over 2. Well, this is sine 50 is like sine theta. While the sine 40 is like sine 90 minus theta, so it's cosine theta. So this is our P in general. And then we have Fx maximum just equal to that, right? So Fs maximum equal to this. And then we know n equal to mg. So mu s equals to Fs maximum divided by n. So just this thing divided by n. So you have 1 over 2 cosine theta divided by sine theta, or 1 over 2 tangent theta in the denominator. Okay. So this tells us there is a inverse relation between angle theta and mu s. So the larger theta you have, the smaller mu s you need, okay, to balance this thing, which makes sense, right? The smaller theta you have, let's say the theta we have here is the critical angle, right? So the smaller angle you have, the smaller theta you have, the smaller tangent you have, the larger mu s you need, which makes sense because when theta is small, this thing gonna like tilted really large, so you definitely need a larger mu s to make sure those are no sliding. On the other hand, when theta is large, tangent theta is large, so 1 over tangent theta is small, so you need only a small mu s to keep everything safe. So the technical message here is, if you want to make sure your ladder doesn't slide, try to keep the angle theta large so that mu s required is going to be small. I guess it's a common sense. You don't have to take this class to understand that, right? So like this kind of situation is pretty bad just by your intuition. You know it's not going to work well. Well, the larger theta you have, the safer you are, basically. Okay. Now in this problem, we do not talk about the person. There's a person on the ladder. There's only the ladder itself, but you can easily add a person to this problem. You know, wherever the person stand, you know, on the ladder, you just have another additional force here, an additional torque given by the gravity of the person, you know, going down either here or here. Okay. Does that make sense to you guys? Okay, let me ask you this question. Which part do you think is safer for the person to stand? On this part, on the left, toward the left, or toward the right? Send me a message. I mean, based on what we learned from here. Is it safer for the person to stand here for the same angle? We put a person on this ladder, right? Is it safer for the person to stand on here or here? On the left or the right? Okay, I got 2 messages. Yes. Yeah, I got 2 answers, both saying left. And that makes sense, right? Again, you don't need to take this class to know that. Unfortunately, whenever you need a ladder, normally it is this part that counts, right? You need to climb to high. Otherwise, you don't need a ladder. So normally you end up here, you know, as a matter of fact. So, and that's the more dangerous part than this part. So you need to be really careful. Make sure your angle theta is big enough so that your coefficient of friction is sufficient to support the ladder, okay? Well, or another way to try to increase the coefficient of friction. If this is on the like some soil or something, you can dig a hole or something, put the ladder into the hole. This will definitely increase the coefficient of friction a lot, okay? Or anyway, just increase the coefficient of friction. That's another way to make yourself safer, okay? So I guess, let me see whether we can do another problem. Yeah, let me quickly do another problem, then we'll do a exercise, okay? So let me see. I want to do this one here, okay? On the beam, okay? There's a person on the beam. So, but we let's see, maybe we don't need to do the whole thing. So there's a horizontal beam of 5 meters long, and weight this much is attached to the wall, by a pin connection. So, and this pin allows the beam to rotate, okay? And then the far end is supported by a cable that makes the angle 53 degrees because it's horizontal. And there's a person of this much weight standing 1.5 meter from the wall. And then ask you find the magnitude of tension in the cable and the component of the force R exerted by the wall on the beam, okay? So this one's, again, a little bit complicated compared with the first one. But let's do this one together, okay? So there's basically a couple of objects here. We have a person, we have a beam, 5 meter, 53 angle. And then the beam is 300 Newton, the person 600 Newton, okay? So this is the example 8.11. Wait, what is happening here? Like, okay. I think it's example 8.11. Okay. So we have this set out. Let me draw the thing here. Okay. There's something wrong with my, okay, here we go. This is the beam we have. Okay, there's a pin here, and then there's a tension here. There's like cable. There's a person here. Okay. Now we need to do force analysis to this to the beam, obviously. So let's do the beam here. Okay. Well, there's always gravity, so there's gravity acting on the middle, and I would maybe call it the WB for the beam, and that is the 300. And then we have, let me double check. So 300, yeah, we have another, we have a person that's 600 standing on somewhere. So this is gonna give another force, okay? What I'll call WP, that's 600, okay? And then there's a tension here at the end here, T, which we don't know. I don't know, okay, what's going on here? So the angle we're given as, I don't know, there's something wrong with my, see, I don't know why it's not going. Sometimes it's right, sometimes it does not. Oh, it's weird. Okay, 53 degree, okay. Well, there's a pin connection here. So what kind of force does a pin give you? It might be any forces, because the pin is something that fixes the whole thing here, you know. When it fixes the whole thing, and then this thing can rotate like this, right? It's not naturally easily a normal force or friction or something. It can be any forces. So in general, we would expect the pin give a force to an arbitrary direction, you know, and we could, let's say we have there could be a y component and an x component, okay? In general, you know, in general, for any force can have these two components. So we put it in general case, okay? So this is our situation here, right? And we're given the length of the beam to be 5 meter, and then the person is sitting like standing at 1.5 meter from the wall. So we have this, I'll just call it L here to be 5 meter, and maybe LB. Well, the person is LP to be 1.5 meter, okay? Let me clean up this part, mess. Okay, so how do we solve this problem? Again, same principle. We use set up direction like this, coordinate system like this, x and y, and we use total force equals 0 and total torque equals 0 as well. Well, in this case, you have a force that's not either along x or y direction, so you need to find the component of the force. Along the y direction, it's going to be like this, ty. So it's going to be t times sine 53. Well, along the x direction, it's going to be t times cosine 53. Okay. So we have a bunch of forces here. So let's set up Newton's law for total force equals 0 here. Okay. So along the x direction, we have these forces, these two forces. We have Rx going to the positive direction minus t cosine 53 going to negative direction. Okay, that equals 0. And then along the y direction, we have more force. We have Ry plus t sine 55. That's the component going vertically, and then minus the two weights, WB and WP, that equals 0. Okay. Again, we have this problem of writing. I don't know why. What is the problem? I need to call the warranty. What? I just simply cannot write anything here for some reason. I've never had this problem before. Negative WB minus WP equal to 0. Okay. For some reason, I don't know. That's crazy. Maybe I'll put Ry here. Ry plus t sine 53. So this is like the second equation we have. Okay. Now the third one we have. Okay, these are the two equations for the force. Now what about the torque? Okay, there's one equation only, right? Again, we need to choose a rotational axis. It's pretty convenient to choose this one here as our rotational axis, because this is a natural choice, because this is the pinpoint. Okay, so we choose this as rotation axis. We have three torques given by these three forces. Okay, these two weight make it go clockwise, so they're negative torques. This tension make it go counterclockwise, so it's positive. So the torque given by tension is going to be T times the distance, which is LB, times the angle between them, which is sine 53. That's the torque. That's positive torque. And then so the torque, okay, this is a positive torque. And then we have two negative torques. Each one of them given by each force. So you have a weight, WB, that's the beam from the beam. Well, the distance here is half of the length of the beam, LB over 2. And then the angle is 90 degrees, so sine 90 is 1. So that's it. And then you have another one from the person, WP. And then the distance is LP. And again, sine 90 is, it give you 1. So it might be my computer's problem. So that is your equation. So you have three equations, 1, 2, and 3, okay? So because we're kind of running out of time, so I'm gonna just solve for T, because this is what is asked in the first part. And then you guys can do 1 and 2 later if you want to solve for Rx and Ry. That's give you the two component of your force at the pin connection. So to get T, you can simply use the third one. To solve it formally, you have T LB sine 53 equals to, you move this term two terms to the right, WB LB over 2 plus WP LP. Okay, so tension itself equals to WB LB over 2 plus WP LP divided by LB sine 53. Okay, now you can plug in numbers here, and I guess I'm going to simplify so that we have time to do our exercise. So in the end, you get basically you take this, you got 413 Newton. Okay, if you plug in those numbers in, you got 413. Okay, I'm sorry about this issue. I thought we lost connection with you guys, but I don't. But for some reason, I cannot see my, I mean, it's still an issue for me because I cannot see my control for the Zoom meeting at all. So there's no control I can do. I cannot even close the class or anything. Okay, maybe I can. No, I don't know what's going on here. So, okay, let's do an exercise and maybe then I can try to fix it. So let's do exercise together. This is gonna be our last exercise for this class. Okay, in this case, let's do a lever problem, okay? We'll try to do it fast so that we have time to, okay. So we should be able to do it like with 15 minutes at least. So let's do it like this. So in the first part, we have this lever here. Let's say the weight, the mass of the lever is 1 kilogram. And then you put a object on one end of the lever, and that object is the mass, it's called capital M. Capital M is 10 kilogram. And then in the first case, let's put the pivot point of the lever right at the middle of the lever. Okay, so the length of the lever is gonna be, let's say 1 meter, okay? And then you apply a force here to balance the lever, okay? It's called F1, okay? So given all this information here, okay, this is the right at the middle. So the question is, what is F1? Calculate F1, okay? How much force you need to balance the lever, okay? This is our first problem, okay? The second problem, the first one is really simple. The second one here is a little bit more complicated. So we're gonna have same lever here, but we're gonna apply, put a pivot point at closer to the object, okay? So this is gonna be, okay, this is gonna be 1/4 of the length. So 1/4 meter, okay? Because the length is 1 meter, so this is 1/4 meter, or 0.25 meter. This will be like basically 0.75 meter, okay? So in this case, same object, same 10 kilogram object, and then try to calculate F2, okay? Go ahead and do this two problems, okay? The first one should be really simple, and the second one is a little bit complicated. Again, using, well, we have two equilibrium conditions, but for this one, let's use this one only, okay? Try to use this equilibrium condition to do this, okay? Remember, tau is defined as FD sine theta, okay? So use this formula for each torque. Find out, do free body diagram, set up your rotational axis, find out how many torques you have, okay, on the lever, okay, in this problem and this problem, and then calculate the torque using the formula, and then set the total torque equals 0, okay? Let's do it together. Sounds good? Again, I cannot, for some reason, I lose that window of showing me and you guys, you know, and so I cannot see either your face from your camera or your reaction or anything. So I don't know what's going on, but there's, so let me just go ahead and do this, okay? So let's do the first one. So if you do a free body diagram here for the lever, you have gravity going down. It's called weight of the lever W. Yeah, I didn't say anything. Okay, so maybe it's mg. So mg here, and then this here is the weight of that object, so mg. There's also a force here that you apply. Well, there's a normal force going up, right, at the pivot point. So there's this four forces balance each other. Now, for the total torque, consider total torque to be 0. We choose this as a rotational axis, kind of natural choice. We choose this as a rotational axis. There's no torque given by these two forces, only this torque and this torque. Okay. So we have tau 1 plus tau m equal to 0. So what is tau 1? This force make it go counterclockwise, so it's definitely positive torque. So I have F1, the force, times the distance, which is half of the length of the lever, times sine theta, which is 90, sine 90, so it's 1. So, well, tau m make it go clockwise, so it's negative. So equal to force times, again, L over 2 as the length times sine theta, which is again, theta is 90, so sine theta is 1, so that equals 0. So very simple relation between these two, okay? Now you notice that the lengths are the same, so they cancel out. So F1 equals to M1G in the first case. So just 10 kilogram times 9.8 meter per second square, okay? So you got 98 Newton. So that's the answer for the first one. That makes sense to you guys? Yeah, please give me some voice response. Otherwise, I don't really know. As I said, I cannot see you guys anymore. Good.
That looks good.
Okay. Now the second part, when you move the lever to move the pivot point to one side of it, you know, the free body diagram is almost the same. Well, one thing you need to notice here is your gravity, center of gravity of the lever stays the same because it's the acting at the lever. The pivot, the normal force moved. Okay, so you can still choose this as your rotational axis. Then there's no torque by this, but there are going to be 3 torques now. You have tau 2 plus tau lowercase m plus tau capital M equal to 0. Okay. Well, these 2 forces make it go counterclockwise, so they're positive. This force make it go clockwise, so it's negative. So tau 2, you have F2 times this length here, which is not half of the L, right? It's like a 3/4 of the L. And then tau, and the angle theta is still 90, so theta is 1. So tau M here is given by the weight of the lever times this. Because this distance is 1/4 of it, so this is at the middle. So this must be 1/4 as well. So this is 1/4 of L. Finally, we have this negative torque given by the capital M. That's again 1/4 of L. So you have the 3 torques balance each other, and the L cancel out, right? So in the end, you have F2 equals to 1/4 of capital MG minus 1/4 of lowercase mg divided by 3/4. Okay, so basically it's a mg minus mg divided by 3. Okay, so this is a 10, this is a 1, so you have 9 times 9.8 divided by 3. That's 3 times 9.8, so you got 29.4 Newton. Okay. Any questions for the second one? Again, if you have a question, send me a message. Okay, I can check the message. So what you see here is, well, the first case, oh yeah, some people forgot about G, which is a normal. The first case, you got a bigger force than the second one. Well, we never use the lever in the first case because we don't want to put the pivot point in the middle. It does not save us anything. But this is just a show, I mean, as a demonstration example. In the second case, as we see here, we need a way smaller force than the actual force of the object to lift it. So that's like, so lever is one kind of a simple machine you can have that allows you to use a smaller force to move something heavy. The reason for that is we take advantage of this equilibrium condition. It's the torques that are balancing each other, not the forces. So if you put this length really large, you could actually have a really small force to lift something really heavy. Sometimes these lengths are called lever's arm. Like this length or this length. And as you see here, the weight of the lever contribute as well a little bit. Okay, not too much, but a little bit. Okay, so basically the idea is by moving the pivot point closer to the object, you could use a smaller force to lift something heavy. Like Archimedes used to say, if I can find give me a supporting point, I can lift the earth. You know, by having a really, really long lever. As you can see, if you imagine there's a really, really long lever at toward the left, you can use a really small force to lift something really heavy. Well, certainly for that to happen, you need to have this lever need to be made of something really, really solid, really strong, so that it does not break by itself. Okay, but this is the idea. Okay, does that make sense to you guys?